Good morning, friends. The last video we had discussed the part of the procedure for the graphical method and disadvantages of the graphical method. Here now we are going to discuss the types of the solution of the graphical method. Here we have the four types of solution in graphical method. Number one is unique solution, and another one is second one an infinite number of optimal solution, an unbounded solution, and no solution. So here we have four types of solutions in graphical method for LPP, for solving of what? LPP. Now I'll explain one example for each solution. So now first I'll take one problem here. Solving of LPP by graphical method. The given LPP of was objective with max z equal to 3x1 plus 4x2, subject to the constraints x1 plus x2 less than or equal to 450, 2x1 plus x2 less than or equal to 600, and x1 comma x2 the decision variables are greater than or equal to 0. So now as per the procedure, whatever the constraints they given, whatever inequality comes in the constraints, first the step one in the procedure we are going to make it as equal. So now after converting this, the first constraints like this x1 plus x2 equal to 450, solving this equation we are getting the points 0 comma 450 and 450 comma 0. Similarly the second constraints is a 2x1 plus x2 equal to 600 equal. See that here the given one is less than or equal to, we converted the first one is what? Equal. And solving this equation, the line equation, we are getting the points, two set of points is 0 comma 600 and 300 comma 0. So now we have to plot this point in the graph. See that here the x1 value, you compare the x1 value, the entire x1 value, the first one, the combination of the set of points is the first one is indicates x1 value, the second one indicates the x2 value. If you're going to see the x1 value, here the maximum comes what? 400. Here the x2 value is also maximum comes 600. So now if you're going to see in this, the x1 in x1 axis, we are considering the one unit of x value equal to 100. We are writing the multiples of 100 because we are having everything is what? 200, 300, 400, 450 like this. That's the reason one unit in x1 axis we are considering the what? 100, 200, the multiples of 100. So we are plotting the point like this. Now the first set of points is what? 0 comma 450. 0 comma 450, and second one is 450 comma 0. 450 comma 0. Now joining these 2 points, we are getting the line equation. This line is called x1 plus x2 equal to 450. This is the first equation. And similarly the second equation, the set of points is 0 comma 600, 0 comma 600, and 300 comma 0, 300 comma 0. So now joining these 2 points, you are getting the line equation is a 2x1 plus x2 equal to 600. After plotting the line like this, we have to find out the region. That region only we can say as a feasible region, solution space, convex region, permissible region. That region we are going to find out. After plotting the point, we have to find the boundary of this given problem, given LPP. Now we are going to start from the point. This is called 0 comma 0. So now here, so how to define the regions are. So now we are going to start from this line. So you are coming on the line, but here now you can't cross the line. This is a line equation of what? x1 plus x2 equal to 400. Actually the original equation they given like this, what? x1 comma x2, x1 comma x2 less than or equal to 450. So your region is lies below to the line. Here x1 comma x2 is 450, but here the original problem says what? Less than or equal. So your region is less than this line. Your region is less than this line. So now you are taking a traveling on this line, but you can't cross the line. Here the given constraint indicates your region is lies below to the line. That's the reason you can't cross the line. You are taking a diversion in this. You are coming to this what line. After that, you can't go straight on this because this is the line equation of what? 2x1 plus x2 equal to 600. Actually this constant is, it says 2x1 plus x2 less than or equal to 600. Your region is lies below to this what? Equation, below to the line equation. Therefore, here your region of the second constraint indicates the region lies below to the line. Line is also included, but below to that. So you are taking a diversion in this. You are coming to this line. You can't cross the line because the line is this, the second line is this, below to this line only. So you are taking a diversion on this. Now then you are coming to this starting point. This is called enclosed region, the convex region, feasible region, solution space. This space only you can say is a what? Permissible region. After finding this region, you are going to find the set of points in the boundary, set of intersection points in the boundary. So if intersection means the two lines are crossing, here x1 and this one. Here the two lines are crossing, you are giving the name is A, and these two lines are crossing in this boundary. These points we are giving the name is what? B. And here this x2 and the equation 1, these two lines are crossing, we are giving the name is what? C. So now we are considering, first we are going to plot the points, the line equation in this graph. After that you are going to find the permissible region, feasible region by using these constraints. See, at the time of fixing that the feasible region, you have to see the constraint inequality. Based on this only you can see that below to the line or above to the line, that two cases you can analyze. Here the equal, but the original consists less than. That's the reason your region is what? Less than this. Here 2x1 plus x2 less than or equal to 600. This equation is equal to 200. Your region is less than that. You can't cross the line. You can't cross the border. That border indicates this what? The constraints. So less than, greater than means above to the line, less than means below to the line. So you are going to consider this is a starting point. Then we are going to take this line, you are going to move on this line. You can't cross this, the constraint is less than, so you are taking a diversion on this. Now you are coming to this, again you can't cross the line, you are taking a diversion in this because this line says below to that. So that's the reason you are fixing your region is this one. This is called a permissible region, or you can say it is a what? Feasible region. After finding that, you are going to consider only that intersection points in the boundary. This is always 0. You don't need to consider that. So except this you can consider. This is the first intersection point is A. That A value becomes 300, 0. The A point what? 300, 0. And B, if you are going to do the same problem in the graph sheet, you can find the exact point of intersection. I am working this one in the white paper. That's the reason I am taking that's one here. 150 is 150, 0. The point of intersection in the place of B, whose vertex points is what? 150, 300. Here the C is 0, 150. So we are finding the only 3 point in the boundary, 3 intersection points in the boundary. After finding the intersection points in the boundary, you are going to substitute these points in the Z. Okay, what is Z? The equation given 3x1 plus 4x2. You are substituting in this what? 3x1 plus 4x2. 300 into 3, 900. Here x2 value is 0. So you are getting the value of Z is what? 900. Similarly, you are substituting the value of x1 equal to 150, x2 equal to 300, you are getting the value of 1650. Then the point of C is here, x1 equal to 0, x2 equal to 450, the value of Z comes what? 1800. Now, in this problem, we are going to consider that the objective. Here in this problem, your objective of the given function is maximization type. Given objective function is maximization type. If it is a maximization given, we have to consider the maximum value of Z. So here we have Z values. The objective function is maximization. We have to consider the maximum value of Z is attained at a single vertex. Here we have 3 vertex A, B, C. Now from this A, B, C, which gives the maximum value in this Z, that we are going to consider. If you are seeing the 3 values 900, 1650, 1800, among these 3, here this 1800 what maximum value. So here this problem attained the maximum value in the single vertex Therefore, this problem has a unique solution because only one vertex gives the maximum value. Through this vertex only the z attained maximum value. That's the reason you can say this problem is unique solution. This is very important. This is an example for the what? Unique solution. So objective function is maximization. That's the reason the maximum of z is 1800. To attain this 1800, here that c whose x1 is what? 0, and the corresponding x2 values comes 450. So this is the first graphical problem. The maximum of z is 1800 and x1 equal to 0, x2 equal to 450. This is the example for the first type of solution is a unique solution because of the only one vertex gives the what? Maximum value. Single vertex gives the maximum value. Now I'll give one more example to the same of the type of solution is a what is unique solution. So now here the maximum of z is x1 minus 2x2 and subject to the constraint minus x1 plus x2 less than or equal to 1, 6x1 plus 4x2 greater than or equal to 24, 0 less than or equal to x1 less than or equal to 5, 2x1 less than or equal to 2 less than or equal to x2 less than or equal to 4, and the decision variable x1 comma x2 greater than or equal to 0. So here the first constraint minus x1 plus x2 equal to 0. Whatever the constraint contains inequality, you are going to convert it into equality. You are giving the name to the constraints 1, 2, 3 like that. Then first constraint comes minus x1 plus x2 equal to 0. By solving this, you are getting the set of points is 0, 1 minus 1, 0. Similarly, the second constraint 6x1 plus 4x2 equal to 24. Solving this equation, the line equation, you are getting the set of points is 0, 6, 4, 0. And the third one is gives in the form of what? 0 less than or equal to x1 less than or equal to 5. So x1 whose lower limit is 0, x1 is upper limit is comes what? 5. Therefore, here you can consider this equation what? 3, and simultaneously the x2 values comes 0 here. Therefore, the set of points comes only 5, 0. The fourth constraint is given in the form of 2 less than or equal to x2 less than or equal to 4. Therefore, x2 is having the what? One value is lower limit is 2 and whose upper limit is at 4. Therefore, we have two set of points in this. So you can read it like this: 2 equal to and what? 2 equal to x equal to 4. So you can put like this: x2 equal to 2 one time and x2 equal to 4 another time. That 2 comes what? One lower limit of that, and the 4 comes upper limit to that. So we are going to plot this point in the graph. See here, we have set of points 1, 2, 3, 4, 5, 6, 7, 8, 7, 1, 2, 3, 4, 5, 6, 7 set of points. We are going to see in the set of points the first value which indicates x1 values, the second one indicates the what? X2 value. Now we are going to plot the points, plot the line and points in this equation. I mean in the graph. If you are going to plot the point in the graph, here see here the first one says 0, 1. Here 0, 1. And the second one comes minus 1, 0. Minus 1, 0. You are joining these 2 points. You are getting a line equation of this. This one gives a what? Line equation of what? Minus 1 plus x2 equal to 1. This gives. Now here the first one says less than. So now here less than means the, so first we will plot the points in the graph, then I will explain what about that less than greater than part. The second equation is whose set of points is 0, 6 and 4, 0. 0, 6 and 4, 0. By joining these 2 lines, you are getting one line equation like this. This is the line equation of 6x1 plus 4x2 equal to 24. And the third constraint, you have only point is what? X 5, 0. So now here 5, 0. This is a one straight line. This one is what? 5, 0. Only you are getting one straight line, x1 equal to 5. And the fourth constraint says 0, 2. And another one is what? 0, 4. You can write it like this. This is a what? 0, 2 and 0, 4. This 0, 4. This is 0, 2. The two also what? One straight line. Now we will come to the constraint inequalities. Based on that only we can define the region, the permissible region where the solutions exist to the given graphical problem where the solution exists for the LPP. It is here the first constraint says is what? Minus x1 plus x2 less than or equal to 1. Here this equation is 1. Less than means what? Below to that. If it greater than 1 means 2, 3, 4 like this. Less than means below to the line. So it says what? Below. That's the reason your region is what? Lies below to that line. Now the second constraint says 6x1 plus 4x2 greater than or equal to 24. Greater than, this is a line equation. Greater than means above to the line. Greater than means above to that. Less than means below to that. So your region is what? Above to the line. That third one is only one. X1 is less than or equal to 5. Here this is what? X1 equal to 5. Less than means what? Below. Greater means above. So now it's very clear, x1 is less than 5. We are going to consider the below to the line. Now the last one is x equal to 2. X equal to 2. X2 lies in between that. Here very clear this. 2 less than or equal to x2 less than or equal to 4. So that x2 is having the lower limit is a 2 and the upper limit is what? 4. Therefore here in between only it says x1, x2 is greater than or equal to 2, less than or equal to 4. So your region is lies in this. Now so we are going to what? Find the permissible region, feasible region. After drawing that line, plotting the points in the graph, we are going to what? Find the feasible region, the convex space, closed space, feasible solution space. See now, to find that here there is a lower point. We are going to start from this. Start from this point of A. You can't cross this line because the line minus x1 plus x2 says what? Less than or equal to 1. You are coming below to the line. That's why you are going to not crossing the line. You are taking a diversion in this. You are coming to this line. And you can't cross this line because x2 values lies what? Here this line says x2 is what? Below to that. Less than or equal to. x2 is less than or equal to 4. So you can't cross the line. You are taking again diversion in this. You are coming what? To this line. You can't cross this line because here x1 says what? The third constraint says x1 is less than or equal to 5. This line is what? X1 equal to 5. Less than means below to the line. So you are taking a diversion again to this line. You are coming to this line. But you can't cross the line because here the last constraint says x2 is having a lower limit is only 2. Okay. So now this is what? x2 is what? X is, it lies in between this. x2 greater or equal to 2. So you are taking again diversion. You are coming to the starting point. So this space is called solution space of the given problem. So after drawing a solution space, you are considering that point of what? Intersections in the boundary. So we are having a this what? 1, 2, 3, 4, 5. 5 set of points. 5 set of intersection points in the boundary. We are giving name to the boundaries. A, B, what? C, then D, E. So we have 5 set of points in the what? Boundary. Set of intersection points. That's very important. Set of intersection points in the boundary. So here the value of A 8 by 3 comma 2. The value of B is 5 comma 2. The value of C, the point vertex C is 5 comma 4. The D whose vertex value is 3 comma 4. And the E value comes what? E point is 2 comma 3. So we have 5 set of points. The 5 set of vertex is what they given. So now we are going to find the value of Z. Z given the given problem, Z value is what? Z equal to x1 minus 2x2. So you are going to substitute in this Z x1 minus 2x2. If you are going to substitute of the A vertex which gives minus 4 by 3, the B vertex given this what? 1, C gives minus 3, D minus 5, E is 2 comma E which gives the value of Z is what? Minus 4. So these are the values we are getting for the Z at the time of substituting this what? Vertex. So that in this given problem, is the objective function whose optimized should be what? Max. So we have 5 points in this. So in this among the 5, which is maximum means the B vertex gives the maximum value of Z. The maximum value of Z comes what? 1 here. Therefore, the optimal solution to this given problem, maximum of z is 1. To get this 1, the set of points in the set of points of B, those vertex of in this vertex x1 values comes what, 5, and x2 values comes what, 2. So in this given problem, the maximum of z equal to 1 and x1 equal to 5, x2 equal to 2. In this problem also only one vertex gives the maximum value. Therefore, the problem is what? This is a type of solution is called unique solution. Unique solution means only one point gives the maximum value of z. That's the reason we can say this type of solution is what? Unique solution. Now, the third example. Solving the following LPP graphically. Solve the following LPP by graphically. Here the maximum of z is 100x1 plus 40x2, subject to the constraints 5x1 plus 2x2 less than or equal to 1000, 3x1 plus 2x2 less than or equal to 900, and x1 plus 2x2 less than or equal to 500. We have three set of constraints in this problem, and we are similarly, as per the procedure of the graphical method, we are going to put equal and giving a name to that equal constraint 1 for the first one and constraint 2 the second, constraint 3 for that what, third. So by giving like this, now you are going to find the set of points. For the first one is what, 200 comma, solving this point we are getting 200 comma 0 and 0 comma 500, and solving the second equation we are getting the points as 3x1 plus 2x equal to 900. Then solving this equation we are getting the point is 300 comma 0 and 0 comma 400. The third one is the given is what, x1 plus 2x2 equal to 500. We are giving the constraint name is 3. Solving this equation, if x1 equal to 0, then the set of points will come 0 comma if you are going to divide by the what, 2, 0 comma 250, and if you are going to put x2 equal 0, then 500 comma 0. So this you are going to solving these three set of constraints. You are getting the points is what, 200 comma 0, 0 comma 500 for the first constraint, 300 comma 0 and 0 comma 450 for the second constraint, and 0 comma 250 and 500 comma 0 for the third constraint. By seeing this set of points, you can see the maximum value of x1 and the maximum value of x2, and by seeing this everything comes multiples of 100. Therefore you are going to consider the one unit of value in the what, in terms of hundreds. So now you are going to draw the line like you are going to writing the points in x1 axis like this and the x2 axis like this, and plotting the points in the graph. First set of points of the constraint is 200 comma 0 and 0 comma 500. So joining these two lines, you are getting this line equation. This is called 5x1 plus 2x2 equal to 1000, and joining these two lines 300 comma 0 and 0 comma 450, 300 comma 0 and 0 comma 450. By joining these two lines, you are getting this what, this line equation of 3x1 plus 2x2 equal to 900. The third one is 0 comma 250, 0 comma 250 and 500 comma 0, 500 comma 0. By joining these two lines, you are getting this line. This is a line equation of what, x1 plus 2x2 equal to 500. See, the first constraint says 5x1 plus 2x2 less than or equal to 1000. So less than or equal to 1000 means your region is lies below to the line. Here 5x1 plus 2x2 equal to 1000. So your region is what, below to the line. The 3x1 plus 2x2 less than or equal to 900. So 3x1 plus 2x2 equal to 900. So therefore your region is lies below to the line. Don't cross the line. The third one is says x1 plus 2x2 less than or equal to 500. So your region is what? This is a line equation of x1 plus 2x equal to 500, but actually the region is lies what? Below to the line. See, now after drawing that, you are going to find the what? Permissible region, feasible region, solution space where the points, the solutions are exist in this. So now after drawing the line like this, to find the feasible region, you are starting from this 0, 0, you are moving on this line, but you can't cross the line. The line says your region is what, below to that. That's why the reason you are taking a diversion to this. So you are coming to this line. Again, you can't cross this line. This line says your region is like below to the line, so you are taking again diversion to this. You are coming, traveling on this line. So now you are coming to the starting point of this is called what? Solution space. This is called solution space. After finding the solution space, you are considering the points, the intersection points in the boundary. So now we have three set of points, intersections points in the boundary. The point of A is 200, 0, and B is 125.187.5, and C is 0, 250. You are substituting these three value in the what? The given objective function of Z. As at the time of substituting this 100x1 plus 40x2, the vertex A gives 20,000 and vertex B gives the value of Z is what? 20,000, and C vertex gives the value is what? 10,000. But here two vertices A and B. Here two vertices A and B give the same maximum value of Z. But here the objective is maximum only. Noted about this. That's the reason we are going to consider among this maximum. But at the time of seeing here, we are getting what? In two values, 20,000, 20,000. That gives the vertex A and also the what? Vertex B. So two vertices A and B gives the same maximum value of Z. Since there are infinite number of points lies between the 2 points. So if you are going to consider A and B, we can find the many values, many points in between that. So we can't say that this is a solution to this. That's the reason we can write simply, therefore infinite number of optimal solution for this LPP. We can conclude this problem like this one. We can't write this, the maximum value of Z is 20,000, maximum is the minimum value of Z is 10,000 like this, because 2 points, 2 vectors gives that the maximum value of Z. So in between the 2 points, many points are lies. That's the reason we can conclude that infinite number of optimal solution for this LPP. Reason is very clear. The optimal values we are getting in A and B, 2 points. So the solution is optimal solution is infinite number of solutions for what? For this LPP. Now continuation of this graphical. Here this graphical, we have that the problem maximum Z is 2x1 plus 3x2. The first constraint is x1 minus x2 less than or equal to x1 plus x2 greater than or equal to 4, and the decision variable x1, x2 greater than or equal to 4. Here x1 minus x2 equal to 2. We are converting all the inequality into what? Equal. We are putting like this and solving that. We are getting the points as 0, minus 2 and 2, 0. Similarly, the second constant we are putting equal to 4 and solving that. We are getting 2 points 0, 4 and 4, 0. We are going to plotting these two lines in this graph. The first one is 0, minus 2. Here 0, minus 2. And the second one is 2, 0, 2, 0. By joining these 2 points, we are getting a straight line just like this. So this line is what? x1 minus x2 equal to 2. Now and that second one we are getting what? x1 plus x2 equal to 4, 0, 4, 0, 4, and the 4, 0. This is what? 4, 0. By joining these 2 points, we are getting this line equation, and this is what? x2 plus x1 plus x2 equal to 4. Here the first one says what? Less than. The first one is what? Here minus 2, 2, 2, less than. Here the minus 2, 2, we are considering this region only, first region. 2 less than is what? This is called less than. Here minus 2, the 2 whose less than comes what? 1, 0. That's the reason we are considering this first. We are considering the first part is what? x1 minus x2 less than. We need less than. That's the reason we are considering this portion. We are considering what? These portions. And here the second constraint which says what, x1 plus x2 greater than or equal to 4. This is x1 plus x2 equal to 4. Greater than means what, this portion only we can say this is what, greater than region. Okay, now this is the region we got, but anyway we have boundary only in this place. Here it goes on like this, there is no end point in this, it goes on like this. Okay, here we can't say this is the end like this, we can't say that the end point of this constraint is fixing only the bottom of that, there is no the upper bound. Here's a lower bound, we can say there is no upper bound for this problem. So it goes and ends somewhere, nobody can define the what is end point for this case. So if it is comes here, the solution space is unbounded because there is no boundary to that. The reason we are mentioning it is what, unbounded. The vertex of this infinite plane A, we can say we can get only two intersection point in this boundary. I mean that the bottom of lower boundary, not in the upper boundary, no boundary in this upper part. That's the reason we can consider only two set of intersection points. One is A, the value of what, A vertex is 3, 1 and B is 0, 4. If you are going to substitute in this Z, we are getting a value of 9, 12. But we can't say that this is a maximum value of Z. We need only maximum value. At the time of substituting in this A and B in Z, we are getting two values 9 and 12. But we can't say that 12 is a maximum value or 9 is a minimum value, because if it is that the region is lies, I mean the solution space exists feasible region, we can define that, but we can find only the lower bound. There is no upper bound, there is no boundary to this given problem of LPP. So therefore simply we can conclude the problem, the solution space is unbounded. This goes on like this, there is no end point to the problem. That's the reason we can say that the solution space is unbounded. The maximum value of Z occurs at infinity. Since the problem has an unbounded solution. Here boundary is there, we can find out that the exact point of the value at maximum Z. Here no boundary to that, the reason we can conclude the problem is unbounded. Right, conclude the problem with the solution of the given LPP is unbounded solution. This is the third type of solution for the graphical method. And the last example for the graphical method, last type of solution to the graphical method. This example for graphical method, the given problem is max Z equal to 4x1 plus 3x2. The constraints x1 minus x2 less than or equal to minus 1 and minus x1 plus x2 less than or equal to 0, subject to the constraints x1 x2 greater than or equal to 0. Now here you are going to convert in the equal, x1 minus x2 equal to minus 1. By solving the equation we are getting set of points as 0, 1, minus 1, 0, and second constraint is a minus x1 plus x2 equal to 0. So now here everything comes what, 0, 0. So this line is passing through the what, origin. So now you are going to plot the point 0, 1, 0, 1, this one. Then second one is minus 1, 0 here. Here this is the constraint says x1 minus x2 less than or equal to minus 1, less than or equal to minus 1, whose less than means minus 1, less than comes what, minus 2, minus 3, like this. So here this portion is comes what, here this x1 minus x2 less than or equal to minus 1. See that, you see that here this less than or equal to minus 1, so minus 1, then whose less than is what, minus 2 or minus 3, goes on like this. That's the reason we are considering only the first quadrant, that's the reason we are stopping up to that. This is what, this part only we can consider. And the second one, the point comes minus x1 plus x2 equal to 0. So if it is comes this line which is passing through this origin only, passing through this origin. Here the first constraint is x1 minus x2 less than or equal to minus 1. We are considering this place. So why we are putting in that line like this, sir? Because the minus 1 less than minus means this portion only. And the second one, x1 minus x1 plus x2, we are solving the equation that goes only passing through this origin. Now here there is no common point to both the shaded region. Here see that this line and the above line and the below line, the two constraints are what, entirely separate. There is no common point in between the two lines. There is no common point to both the shaded region. So we can't find the convex region for this problem. So the problem cannot be solved. Hence the problem have no feasible solution. So we can conclude the problem like this: no feasible solution. Especially in competitive exams, they may give this type of problems only. So that's the reason you be very careful while solving this type of problems. So they will give you different solution, unique solution or unbounded solution, infeasible solution, and no solution like this. If it is given, you can say that the correct solution to the given problem, this type of problems, is what? No feasible solution, because of this no common intersection points available to this given problem. So now this is the fourth types of solution example. Thank you.